the recording. Okay, I'm starting the recording. So we talked last time about, Section 1.8 dealt with linear transformations. And we learned that actually, if you take if you define your transformation on a vector as the matrix A times a vector X, okay, if you do that, that is a linear transformation, because if you that defining your transformation that way satisfies the two properties of linear transformations. So the question is, now we're looking at what transformations can do. And in graphics, transformations can be used. You can represent figures with pixels. Like if you have a two-dimensional figure in the XY plane, you can have points on the figure that represent the figure, maybe 1,000,000 points. And by transforming the points, you can do different things. So we had talked about how we can, but then what is the matrix that's going to do the job? It's called the standard matrix. So we learned that for this problem, reflecting points about the line x2 equals x1, that the standard matrix, I'm just reviewing a little bit. We're going to go to a new problem. We learned that we can take the E1 and E2 vectors, which correspond to the ij vectors, and study the transformation of those vectors. And like, for instance, the 0.10 got mapped to 0, 1. And so the transformation of E1 was E2. And then the 0.001, the j vector, which we call E2, gets mapped to 1, 0. So the transformation of E2 equals E1. And then, of course, now that we got that, Theorem 10 said if you want to figure out what your standard matrix is, the column vectors would be the transformation of E1 and the transformation of E2. It would be those two vectors. And that's how you got the matrix 0, 1, 1, 0. So in Table 1 in Section 1.9, they show a lot of, it's towards the back of the, well, actually, hold on. It was from, hold on here. Let me see here. Section 1.9, they had a goldfish that was getting transformed in different ways. And that was on pages 74 to 75. And so they show a lot of standard matrices that'll do the job. Every one of them, if you just follow this approach, look at the transformation of the E1 and E2 vectors, find out what those vectors get mapped to under the transformation. The map vectors, then, you can use those to construct your standard matrix A. And that's what we had learned. So what I'd like to do now is I'd like to go to another example. Okay, I'd like to go to another example. And let's do this example here. All right, so take a moment to copy this example down. So right now, don't the orientation quiz. I'll make an adjustment. Don't go into the quiz now. Okay, so now this is an interesting problem. We want to find the standard matrix, okay, of the transformation, and the transformation maps r squared to r squared, and it's going to first rotate points -3 pi over 4 radians clockwise, and then it reflects points through the horizontal x1 axis. So that's right, Binyam. Well, we actually have, you have two transformations going on that you do. That's right, Binyam, you do. And first of all, -3 pi over 4, how many degrees is that? Pi over 4 is how many degrees? 45. 45. So 3 pi over 4 then, if pi over 4 is 45 degrees, 3 pi over 4 is 135 degrees, but it's -3 pi over 4. So we have a -135 degrees. And does that mean we are rotating? Well, they're being nice there. They're telling you it's clockwise. All right, and that will put us in the second quadrant. So let's go ahead and let me show you how to do this one. What's like really helpful with trigonometry? What's really helpful? I mean, what helped us a lot on the previous problem from section 1.9, the previous example we did? I mean, offhand, do you know what the matrix A is? No, right? So Robin's right. We definitely want to draw a diagram. We definitely want to draw a diagram. Okay. So, all right. Let's first of all take a look at the E1 vector. The E1 vector is located at 1, 0. Now what we want to do is rotate the point well, I want to say it the right way. We want to rotate the vector negative 135 degrees clockwise. So that's going to move 1, 0 to this coordinate here. All right. But of course, we have to think about, all right, well then what's the new coordinate? What's the new coordinate? Because we know that the matrix A is going to be, the column vectors are going to have coordinates, transformed, transform coordinates. So what we can do is, okay, well, we might have to recall our trig days, but, we can, make a reference angle here, a right triangle, and what's the reference angle going to be for this right triangle here? What's the reference angle? How many degrees is it? Actually, hold on, I didn't do that quite right. I didn't do that right. This is your, so to get your reference angle, you connect it with the horizontal axis, right? The triangle gets connected to the horizontal axis. But it's still 45 degrees. Yes, very good. That's still 45 degrees. Okay, there's the reference angle. And so the coordinate is going to be negative root 2 over 2, negative root 2 over 2. So you might have to, if you have to remember these, your unit circle. On the internet, they have, if you just type unit circle in trigonometry, go to Google and do that, up will come a bunch of unit circles with all the markings on them. So I've done the negative 135 degree rotation, but now what I have to do is I have to take this vector, and I do it with vectors. I take the vector and now reflect it about the x1 axis. And so negative root, this coordinate negative root 2 over 2, negative root 2 over 2 gets mapped to negative root 2 over 2 and positive root 2 over 2 because we're in the third quadrant. So the vector E1, which is 1, 0, after everything's done, the transformation is negative root 2. Oh, yeah, I think that's right. Hold on. Yep. Yeah, thank you. This here is the second quadrant. Thank you. And this is the third quadrant. That's right. Thank you. Thank you for catching that, Binyam. So E1 is defined to be 1, 0. Okay. E1 Moshe is defined to be 1, 0. E2 is defined to be 0, 1. And it's not in the question, but the way you come up with the standard matrix A is you transform your E1 and E2 vectors. That's what we did in the previous example. We're doing the same thing here. Now there's a discussion in the chat window about my quadrants. I mean, I know my quadrants. Those are the quadrants. So ultimately then the vector E1 gets mapped to negative root 2, positive root 2. Are there any questions so far? All right, well, let's now, but we have a 2 by 2 matrix, so we need another transform vector. So now we're going to take and I don't want to make it too small, but I don't want things to like disappear, Now we're going to take the E2, that vector, we're going to rotate it clockwise, negative 135 degrees. Okay, when we do so, we'll draw in the right triangle. I don't know why that's not. Come on, give me a line. That's fine. What's the reference angle for this triangle here? Again, that's right, Matthew. Again, it's 45 degrees. So the coordinate here at the tip of the vector that's got transformed is got to be √2/2, negative √2/2. But then remember what you're going to do. Now you're going to take that vector and reflect it about the horizontal axis, x1. And so √2, negative √2 becomes finally negative √2, or positive √2/2 and positive √2/2. And so the E2 vector gets transformed to √2/2, √2/2. Okay. And this is the kind of work I would want to see on, this section 1.9 is not on your first exam, but it'll be on your second exam. And this is the kind of work, the justification I would want to see. Okay. So how do we show which transformation we did first? Well, you're starting at E2 here, and you're rotating it. You got to do that. You're told that you're doing the rotation first. So you do the rotation first. Well, this is fine. This is fine, Matthew. What you see here? This is fine. This is showing me enough. The work here. Okay, so are there any questions? Are there any questions on what you see here? Okay. Okay. Yeah. Yeah, and then let me know when we're ready to move to the next page. Moshe's ready. Okay, thank you, Moshe. Is anybody still copying? All right, Matthew's good. Okay, well, if everybody's good and Francesca's good, well, then let's get to our answer. Well, actually, it's right down here. I don't have to go to a new page. It's right here. So again, we're using that theorem 10, and the column vectors of our standard matrix A for the transformation are the T of transform vector E1, transform vector E2, and that gives us this this matrix here. All right. Are there any questions on that at all? Okay. Okay. All right. So let me see here. All right. So one of our students brought to my attention an exercise in the multiple choice, section 1.9, exercise 29. It's a multiple choice. Well, it's like a select the answer kind of one. And I want to investigate that a little bit further before I talk about it. I have, just to be honest, I've just not had the time getting this quiz ready and everything. But I will, you know, if I don't, you know, have a chance to talk about it tonight, I won't forget. And on Monday, I'll talk about it. It's section 1.9, exercise 29. So, you know, a lot of the things that you're learning are very conceptual in sections 1.8 and 1.9, but I always find it helpful to you know, come up with like an example, if like particularly those multiple choices. And I already showed you, we already talked about that, how it helps. How many of you find it helpful to kind of, if you're trying to disprove something, to come up with an example that disproves something? How many find that helpful? I find it extremely helpful. Yeah, and that's something that you have to do with these multiple choices. And a lot of you I see are doing that. All right, that being said, I want to talk a little bit about section 2.1. Section 1.10 actually is a very nice section. It deals with models in business science and engineering. But the one there's one model in there that deals with it's called hold on, migration matrices, and we're going to be seeing that later on. So the at least one very important application from section 1.10 we're going to see later on in the course. Okay, but we do have to move into chapter 10 and chapter 2. Sorry. So let me stop the recording here.